Remote people, how's the mic? If one of you guys can hear me and give me a like thumbs up or something, so the mic is working. Test microphone. Okay, cool. All right. I don't know. There's one on the 3rd floor, and that's where my office is. So I don't really know if there's one down here. Okay. Yeah. So the elevator is the kind of middle one. Okay. Cool. All right. So let's get going. All right, let me check on people here. I'm Jojo. Okay. Christoph. Benjamin. Hope. Noah. Anna. There. Nicholas. AJ. Kaylee. Alexander. And Keyshawn. Okay. And Patrick. Okay. So, where we were talking last time was about certain kinds of trig limits. So first of all, we saw things like this. The limit as x goes to, say, 1 of 0 of x squared plus 6 times sine x. And what we can do is, we know these limit rules, we can evaluate these separately. So here we could think of the limit as x goes to 0 of x plus 6, and then separately the limit as x goes to 0 of sine x. And both of these separately are kinds of limits that we can find by evaluating them. And that means that this first one is 6, 0 squared is 0, sine of 0 is 0, so this limit gives us 0. Okay. A more complicated kind of limit that we found was the limit as x goes to 0 of sine x over x, and this limit is 1. This we're kind of taking as a sort of black box. The textbook has a way of showing where this limit comes from. We're not going to really worry about that. We'll just take it as a given. And what we can do with this is, if there are other trig limits which are indeterminate forms, and this one, if you put in 0, you get 0 over 0, so it's not one we can find by evaluating. But if there are other trig functions with indeterminate forms, we can try to find this limit inside it, and then hopefully we can deal with whatever else. So part of the limit will be sine x over x, which is 1. Everything else, hopefully that's a type of limit that we can evaluate using other means. So for instance, that would be something like the limit as x goes to 0 from the right of sine x over x squared. So in this is an indeterminate form. If you put in 0, you get 0 over 0. But looking at this, we can say, well, there are 2 factors of x on the bottom. If I separate this, if I separate one of those out, then what we can get is approaching 0 from the right of sine x over x times 1 over x. So that's just algebra. That's not any kind of limit thing. And this is what I mean by finding this limit inside other limits. Looking at this, we can say, well, sine x over x, we know what happens to that. We know that this limit goes to 1. So then we really just have to think about what happens to 1 over x. And if we're dealing with 1 over x, the way to start is what happens by putting in 0. And putting in 0, we see, if we didn't remember the graph already, 1 over 0, that means that there's an asymptote here. So that says shift into the asymptote mode of finding limits. And what we have to check is, are we getting positive or negative numbers on the bottom? If we're putting in things that are greater than 0, we're getting positive things here because it's just x. So what's happening is 1 over x is going to infinity. That's the way that we interpret this. And so where you're taking something going to infinity, multiplying it by something going to 1, and multiplying by 1 doesn't stop something from going to infinity. In fact, if you multiplied by 1,000,000 or divided by 50 or something, those don't stop something from growing to infinity. So this limit is infinite. Because we really look at the 2 pieces separately. This goes to 1, this part goes to infinity, and combined, something going to infinity times something that's leveling off anywhere other than 0, that's going to go to infinity. There's another way where this gets used, and this kind of showed up at the very end of class last time, but we didn't really see an example with it. So more generally, what we can say is sine, and this is the way I wrote it, sine of something divided by something goes to 1 as that something goes to 0. What the takeaway from this is that it doesn't have to literally be x inside here. If you have something inside of sine and you divide by that same thing, then as long as that thing goes to 0, the limit's going to be 1. So that means that if I write something like this, the limit as x goes to 0 of sine of 2x over 2x. This is not literally this limit, but it's the same kind. The same thing is in sine as in the denominator, And if x goes to 0, 2x also goes to 0. So this limit is 1. If we tweak this a little bit, so the limit as x goes to 0 of, let's say, sine of 6x over x, now we're not in this position yet. We have different things inside sine and in the bottom. But if we had a 6 on the bottom, then we would be back in this kind of case here. So the move that we can make is put a 6 in the bottom. The way we can do that is by multiplying and dividing by 6. This is 1, so it's not changing the value of the function at all. But what it's doing is giving us some extra numbers around, so we can say this 6, we really want that in the bottom. So it looks like this. This top 6 is just the cost of getting the 6 on the bottom that we want. So this is 6 times the natural log of 6x over 6x. And now we can say, focus on this function. This function goes to 1, just like this one did. And multiply that by a 6 afterwards, since this is a constant. So this is 6 times 1, which is 6. Questions about any of these kinds of limits? Because especially this one, which is the newer, kind of the newest thing. Okay. So then we can handle some trig limits, which is a good development. But we can't do everything yet. So what is this limit? The limit as x goes to 0 of x squared sine of 1 over x. This question is rhetorical because we don't really know how to deal with this yet. If we try, what we'd seen a few places in here is, we'll look at the two pieces separately. What do they do? X squared, as x goes to 0, that goes to 0. But on the other hand, what is sine of 1 over x? That was this function that oscillated like crazy. You got close to 0. So this function, the limit doesn't exist. And the way that those limit rules were phrased was, if you know that the two limits exist, then you can find them separately and then multiply together. Here, this limit doesn't exist, so we just really don't know what to do. It seems like this limit might not exist, but in fact it does. And we need a way of coming up with that fact and then seeing what the value of the limit actually is. So what we need to do is we need a more high-powered tool to evaluate some limits, which will be especially well suited for this kind of limit. And so this is what is called the squeeze theorem. What this is going to look like is it's going to say, you want to find this limit? Don't worry about it for a second. Check some other stuff. If you check things and things work out in a certain way, you'll be able to say what this limit is. But we won't be directly dealing with it like we did in these examples. So first, I'll say what the squeeze theorem is. I'll draw a picture giving you some idea of why it might be true and also what it's saying. And then we'll talk about how we can use it and then apply it to this limit. So here's what the squeeze theorem says. It says that for functions f of x less than or equal to g of x less than or equal to h of x around but not at a. So where there are going to be three functions, a bottom one, a middle one, and a top one, and this inequality holds at least around some point A. And then, as always, we don't care what happens at the point A, so maybe it's not, the inequality doesn't hold there, but in some kind of interval around that point. Okay. So what we look at is if you look at the limit of the bottom function, and that exists and is some number L. And that L is also the limit if you take the limit of the top function. The limit as x goes to a of h of x. Then what you get to say is this L, which was the limit of the bottom and the top, that is also the limit of the middle function. So this is what I mean by not doing this directly. If we have this inequality of functions, if you check the limit of the outer two, you get to conclude the limit of the third one also, if the outer two agree. And this really, I think, is kind of best hits home through a picture. So suppose we have this graph. There's some point A, there's some function f here, there's some other function which will be h. Their limit is the same at this point A, which is over at L. And then what we're saying is, suppose there's some function that is stuck in between them. So this would be something like, who knows? There's some function g stuck in the middle of them. And often this g is maybe not very nice. But what we can see happening is because it's always stuck between f and g, or f and h, sorry, and f and h have the same limit, as we get closer to this point A, it's squeezed between them. And since h and f are going to the same height, there's no room for this g to do anything other than also go through this height L. So that's the picture of what's happening and why it's called the squeeze theorem. This inequality and the fact that they meet up at this point A at height L says G is forced to do that same thing. So this is what the squeeze theorem is saying, but how do we actually use it? Which is a good question. So here's how the squeeze theorem is used. So the first part is you start with the limit as x goes to a of g of x. You want to find. And I'm using this notation purposefully. The way that you'll use this is there's a limit you want to find. You're going to think of that function as the middle function here. Because the way this is set up is you check some things and then you get to conclude the limit of g. So next up is you have to say find, pick, take, or choose somehow functions f and h. So you have this inequality. So this is something that is part of the work involved. Come up with some functions that are both bigger and smaller than the function in the middle that you started with. Then what you do is you take some limits, but not of g. That's the hard problem we started with. Look at the outer two. So evaluate the limit as x goes to a of f of x, and the limit as x goes to a of h of x. So we have a limit at some point a. We're using that same point for the outer two functions. And when you find these two limits, if you're using the squeeze theorem correctly, you'll want to see that they agree. And then that's all the work you really do. At the end, there should be some kind of wrap-up line saying what you did. So by this squeeze theorem, the limit that we wanted from the very beginning, the limit as x goes to a of g of x, is the same as the other two. So this is the procedure that will work, and we'll apply this for that theorem that, limit that I just erased here. So other than how does this look in a specific case, are there any kind of clarifying questions that I can answer before we see it? Okay. It might be unclear exactly how all this works without the example, so let's get into it. So that limit we wanted to find was the limit as x goes to 0 of sine x, or x squared sine of 1 over x. So what we need to do is we need to find an inequality with this function in the middle. This x squared sine of 1 over x is going to be our g. We need to come up with this f and h. As a first step in this direction, and this is why the squeeze theorem is really well suited for limits with sine or cosine in them. One thing that we know is that even if we have 1 over x in there, sine is going crazy. Sine as a function only ever gets up to 1 and down to -1. So whatever values it takes, it's always stuck between those two. So this is by looking at the graph or thinking about the range of sine. No matter what you put into sine, it only gets up to 1 and only gets down to -1. Which is true, but not exactly what we wanted, because we want this function in the middle. But we have part of it, so let's take this inequality, which gets us halfway there, it seems, and multiply everything by x squared. Multiplying by x squared keeps the inequality in the same direction because x squared is greater than or equal to 0. And so now we get minus x squared is less than or equal to x squared sine of 1 over x is less than or equal to x squared. And that is the kind of inequality that we want. It has the function from the original limit in the middle, and the outer two are much, much simpler. And that's really why this thing works, is you say, I really care about the complicated one, but you put it between two simpler ones, and we can actually evaluate these two functions. They're polynomials, so they're really easy to deal with. And that's what happens in this next step. Actually evaluate the outer limits. So the limit as x goes to 0 of negative x squared, polynomial, just put in 0. The square and the negative don't do anything. So that's 0. And we don't even have the negative on the other side. So the limit as x goes to 0 of x squared is also 0. And that's what we wanted to see. We wanted these two limits to give us the same number. Because now, this is what the squeeze theorem says. If you have an inequality and the outer two functions have the same limit, the middle function has that same limit. So the way that we end this is a real English sentence with punctuation and grammar. So this would be something like, so by the squeeze theorem, the limit as x goes to 0 of x squared sine of 1 over x equals 0. So giving me not just the answer, which you need to also tell me this limit is 0, but you want to explain why. Because you looked at some things and on their own, they're just true things. But you really want to say the squeeze theorem is this fact which lets me take all this stuff and draw the conclusion that the limit I wanted to find from the beginning exists and is actually 0. Questions about that problem? Okay. So the squeeze theorem is complicated and not something you want to try from the very beginning. Things like evaluating, doing some algebra, those are the main ways. Where the squeeze theorem really shows up is trig limits that don't exist, like sine or cosine of 1 over x and things like that. Where it could also show up would be, how far? If you were given some problem like, if x plus 1 is less than or equal to g of x is less than or equal to e to the x, find the limit as x goes to 0 of g of x. So some phrasings of problems that you might encounter would give you an inequality. And if they give you an inequality, that just screams squeeze theorem, because they're really telling you, here's this inequality for free, you get to start in the limit stage by just dealing with the outer ones. But the case where you might have to come up with an inequality on your own is largely going to be these kind of trig function limits. Last squeeze theorem problem or questions. Okay. So now we're going to kind of swing the other way. Here we've gotten into some complicated looking limits that take some special techniques. What we also want to think about is, when are limits easy? So the easiest way of finding limits is when you just get to evaluate the function. And when do we get to do that? The way that we will think about that and phrase finding limits by evaluating is talking about continuity. Sorry, there's going to be a lot of words with a lot of vowels, and I'm going to have to try to spell them correctly. So if you think about maybe pre-calculus or before, if a function being continuous, what that means it's meant something like you're drawing the graph and you don't pick up the pencil. So you can't kind of jump around or do anything. It's just one continuous line. But when mathematicians were thinking about this 150 years ago or something, that really geometric picture isn't good for proving things about continuous functions. So there was some argument and debate, and they tried to figure out what's the right way to say what it means to really be continuous. And the right way is really using calculus, and finding limits is easy. So what we'll say is that a function f is continuous at a point A if the limit as x goes to A of that function f of x is equal to f of A. So you find the limit at A by evaluating. And graphically, this is saying what the function does as you get close to A is that it goes to where it actually is at A. So this is what we'll mean by something being continuous. And actually, there's a lot of information packaged in here, if you look at it the right way. So if the function f is continuous at A, there are three things in particular we know that just come from this equation. By thinking of this equation as saying there are two numbers that exist and they are the same. So first up is that f of A exists. Or said in another way, A is in the domain of the function. So if your function isn't even defined, it's definitely not continuous, is kind of the takeaway. So we'll still be caring about the domain, but even if you're defined, you might not be continuous. Another thing that's involved in here is that this is saying the limit as x goes to A of f of x exists. So to be continuous, this side has to mean something and the limit has to exist. So all of this time we've been finding limits. One way that it gets used is that if there's a place where the limit doesn't exist, your function is definitely not continuous there. So 1 and 2 say both sides of this equation are defined as numbers, and the third part is that the limit and the value of the function are actually the same. The reason for laying it out like this, which is you might think of as overkill, is that if we kind of turned this around and wonder where's a function not continuous, then what we can say is if any of these three things are broken, if they're not true, then your function isn't continuous there. So these are really laying out what things are you looking for where a function might not be continuous. So if any of 1 through 3 fail, f is not going to be continuous at A. Some other ways of phrasing this is that f is discontinuous at A, and also as the kind of adjective for A version, A is a discontinuity of f. Like I said, lots of vowels, and spelling on the board is always a little difficult. So these are just some ways of phrasing. So we could be asked, here's a function, find all of its discontinuities. That would be finding all the places where your function is not continuous. And how we can start is by looking at a picture and thinking about graphically, how do these things appear? So here's a big function. We'll say, got something there. And then we come down and we're here. So I'm definitely not going to have a formula for this. And I'm not even going to really worry about y values. Just kind of giving us some function f to look at. And this is kind of where I wish I had a little more board space. So I'm going to try to keep those on there for as long as I can. So the question is, for this function f, what are some x values for which it is not continuous, and why? The why being which of these three properties is being broken or is not true at a particular x. So we'll say discontinuities of f. So what's some x where it's not continuous and why? -2y. That is, yeah, that's one of them. So which of these things is not true at -2? 2, the limit doesn't exist. Yes, so at 2, what's happening is there's this vertical asymptote. Well, you could also say, and this can be the thing, more than one thing might going wrong, there the function doesn't even exist. So f of a and the limit don't exist. But even if I said, okay, let's put we have an asymptote, let's put a little point down here on the x-axis, that would fix the function not being defined, but there'd still be an asymptote. So in this number 2 saying the limit exists, this means is a number. So this doesn't include infinity or minus infinity. As some other terminology, which is not the most important, but is sometimes handy to have around, is x equals -2 is sometimes called an infinite discontinuity because there's a vertical asymptote. So if one of the limits is infinity or minus infinity, that on its own means the limit doesn't exist, and then you're going to have a discontinuity. So what's another one? What's another point where it's not continuous, and which of these is being broken? 1. Which one is wrong at 1? 3. So it's right. So it's not 1 because the function is defined down here. I would say a little more basic than that is that the limit doesn't exist, which if the limit doesn't exist, definitely they're not equal. So here, I guess it doesn't exist because the two sides aren't going to the same place. So in this phrasing, it's kind of assumes this limit exists, and we have a problem before we even get to that where there's this jump. So here, why this limit doesn't exist is, we've seen this in a few cases, as you go from the right, you're going up to this hole, whatever height that is. As you're coming from the left, you're going down to this dot, whatever height that is, and those numbers aren't the same. So, right, so this thing doesn't exist, and maybe the most basic reason is the limit doesn't exist. And graphically, that's this gap. So x equals 1 is the limit as x goes to a, or 1 of f of x doesn't exist. There's some terminology for this case too. This is what's called a jump discontinuity, which matches pretty well because there's that jump. Exactly what is making it a jump, though, is that the one-sided limits exist, but are different. Which is, I think, good to explicitly point out what's making it a jump, because we've seen other ways where the limit doesn't exist. So that would be something like that sine of 1 over x, the oscillating like crazy one. That's a case where the limit doesn't exist, but not because there's some jump. So the last one is x equals 3, which is really property or case 3 right there. So x equals 3 is where the function value, the dot, and the limit, which is the height we're going to here, are different. So the limit does exist. Both sides are heading towards this hole. The function exists because there's a dot there, but the limit and the point are different. This kind of limit is what has a less helpful name. This is what's called a removable discontinuity. And the way this is described is that the limit exists, but the function isn't continuous. Graphically, what happens in these situations is there's a hole. So if the limit exists, that means your function is heading down towards some height from both sides. But if you're not continuous, that means the point is somewhere else, or maybe it's just not defined at all. Either way, you have a hole. So these three things, holes and jumps and asymptotes, we've seen in taking limits. Those are the kind of complicated cases where we have to do some extra work to figure out what's going on. And so those are the most common ways where we get discontinuities here. Or here or in any function. These are the things that are happening. And in dealing with just the formulas, these are the things that most likely happen. You get an asymptote, or the two one-sided limits are different, or you have a point that's not in the domain, which causes the function to not be defined. There's a little more terminology which we want to introduce so we can keep being careful and precise when we're talking about continuity. So bear with me for a bit while we lay this out. So first up is that a function f is continuous at a from the left if you take the left-hand limit of f of x as you go to a, you get f of a. And similarly, there's a version of this from the right. You can be continuous to the right if you take the right-hand limit. What this is getting at is, like with one-sided limits, you might say, okay, the limit might not exist, but one side or the other side is well behaved. Here, this is saying maybe it's not continuous, but one side is doing what it should. So this is a kind of special, or this is a case where you might not be fully continuous, but maybe from one side you will be. Which is going to be far less prominent than continuity, but it's good to at least know that this is a thing which you might have to think about. In this big example, a place where this one-sided continuity is happening, this function is continuous from the left at x equals 1. So that's saying at 1, there's a jump, so it's definitely not continuous. But if you were to just look at the left side, the function's going down and there's the point, so it's doing what it's supposed to. And sometimes that's useful to know that one side or the other is holding up its end of the continuity, but if you look at both sides, there's a problem. 3 at x equals 3, this isn't continuous from either side, because even if you just look at one side or the other, the limit is up here at the hole, but the point is down here. So this doesn't have one-sided continuity either way, even though the limit exists. And as one last kind of definition of laying out ways to talk about continuity is, so far we've really been saying, are you continuous at this point? So this function is continuous at 0 because it's going down. The function has limit where the function actually is there. It's not continuous at 1 because the limit doesn't exist, and talking about it point by point. What we'd also like to say is identify all the places where it's continuous. So collect all of the points of continuity into an interval. So as the last way that we'll describe talking about continuity is that a function is continuous on an interval if it is continuous at every point of the interval. So we can ask a question, where is the big example continuous. And I've written continuous enough, I'm going to abbreviate it some. Where is this big example continuous? So what this means is write down an interval or something in interval notation which covers all of the points. Or kind of reversed is you want to identify where it's not continuous and throw those out. So we figured out it's not continuous at -2 because of the asymptote, 1 because of the jump, 3 because of the hole, but we want to include every other point. So in interval notation, what that would look like would say, well, we want to go all the way down because it's kind of assumed what's left here is fine. But when we get to -2, we want to skip over that. After -2, we're good again until 1, where there's the jump. After 1, we're good again until 3, where there's the hole. And then from 3 to infinity, because again, once we get past that hole, everything is fine. Something to, hopefully saying this doesn't make it worse, but something you don't think about is we said that the function is continuous from the left at 1. Here, we're just saying we're only looking for points where you're really both-sided continuous, and so 1 doesn't count. What's constructive, or I think a good comparison to do, is compare this to the domain. So if we looked at where this thing is defined, -2, no, because of the asymptote, but at 1, we have the point. At 3, we have the point. So being in the domain, you at least, if you're going to be continuous, you have to be in the domain, but you can be in the domain and not be continuous. So for the domain, the only bad point is that asymptote. So we're -infinity to -2, and other than that, we're good. So we just have to skip the 1 point at -2, everything else is fine. So this is kind of giving us an idea of graphically how does continuity or discontinuity look. The next big thing is, well, which functions are continuous on their domains? Because if we know a function is continuous, then limits are easy because you just evaluate and you're done. So that's where we'll pick up next time. Okay, then make sure you check out the announcement that I posted, kind of laying out what to expect for the week. And I will see you guys in lab tomorrow or Wednesday. And if you have lab tomorrow, there's not going to be any continuity stuff on it. It'll just be limits of the kind we were doing last week. Yes, tomorrow's 1:30. All right. If any of you guys have any questions.